1, 2, 3, prova. 1, 2, 3, prova.
Aspetta, Scusa, mi sono incartata. Sono fuori da tutto questo. Scusa l'entusiasmo.
Io già mi vedo in streaming su YouTube.
Cosa?
Già mi vedo in streaming su YouTube.
No, voglio sempre l'audio. Stacca un attimo il tuo audio.
Good morning, dear friends. We will start in 5 minutes. We wait 5 minutes to see if other people will connect to this section, first section of ASIAM 2021, and we start according to the program. Thank you so much. words as introduction of this ASIAM 21st. I mean, it was a long process to reach this conference with a lot of challenges due to the pandemic. And of course, we had preferred to make the meeting in presence, but due to the uncertainties due to the pandemic, we are almost constrained to prepare the conference online. But first of all, I want to thank TUVN for the strong support that they have given during all the process. In particular, the group of Jürgen Stamfel that was completely involved in all the choices for the conference. We always discuss during the preparation of the conference the mode and modality for the conference of this year, and at the end we convert to the decision to go completely online due to some restriction in different countries. So I want really to thank him for all the support and for the preparation of this conference. That was really an honor to work with all his team, and I think the support that they have given to the conference is really highly appreciated from all the participants. After that, I want for sure to thank all the chairmen of this conference. And so I want to mention first my colleague in NTNU, Jan Torgersen. I want to mention Professor Lucas Soesmel from University of Sheffield and Breck van Overeverde from KU Leuven. Also, their support was highly appreciated during the preparation of the conference. And of course, the conference will not be a success without all the participants that have registered to the conference that will attend the section and will be present online, presenting their work and making discussion about the interesting topic that we have in the conference. And in particular, among these participants, I want to thank a lot the plenary speakers, the 6 plenary speakers that give the availability to make the long presentation for this conference, so the plenary speech. And I want really to thank them for the support and the continuous help that they have given to the conference. We had in the conference 120 presentations from 25 countries. After the edition of Trondheim, I think this is quite successful because I mean, people are quite tired about online conferences. And so it was not easy it is not easy to attend all these online conferences and to be present all the time. So really, we thank all the participants. I also want to thank a lot the support of European Structural Integrity Society. The conference is organized under the umbrella of ESIS. And so I want to thank in particularly the president of ESI, Francesco Iacoviello, that has helped during all the process of the conference, also during the decision process that actually was to make the conference online, and all the support that he has given during the preparation of the conference. After that, I think speaking about the technical part of the conference, we have different nice topics. The conference is dedicated to structural integrity in general. So we have some sections that are dedicated to fatigue, some sections that are dedicated to fracture. And also we have a variety of materials that are considered ceramic, composites, and metals, and the light alloys. So we have a high, variability or high range of topics that are treated during the conference. I hope that you will enjoy all the sections. The program, we've tried to make the program at the best of our capability. Of course, there are in some cases, only 2 cases, some parallel section to stay inside the 3 days of the conference, because there is another conference next week that is quite big and online, so we cannot go in the next week. But I hope that you enjoy in any case the program. We try also to be flexible with the submission of the presentation, and actually the last update of the program was made this night. So we try also to help the authors and all the people that want to attend the conference to be present today. So I'm the chair also of this section, and now I want to introduce you the second speaker that will give you the welcome of this conference. That is Professor Francesco Iacoviello from University of Cassino. He's the president of European Structural Integrity Society, and so I welcome him to give a short speech of introduction, and after that we will go to the first plenary speech by Guyan Kian. Thank you so much.
Thank you, Filippo. It is always a pleasure to join you in this wonderful event. At least I'm checking the streaming. At least we can meet virtually, because with this pandemic, it is always complicated to organize event in presence. Well, as you know, ASIS is an important association, and it is based on the activities of national groups and technical committees. Thanks to technical committees, we were able to organize many virtual events like this one. We will have also in the next days many other important events, for example, the one organized by TC4 or the other one organized by TC3, the crackpots, in 2 weeks. Just a few words about this event. It will be organized on Zoom, as you can see in this room, but we will also stream this event in our YouTube channel and in Facebook pages, the ASIS one, and the IGF one, the Italian Group of Fracture. And we think that it is really important to spread our discussion, to help people to join us. Obviously, the streaming will not allow to participate to the discussion, because only a registered participant will be able to join the discussion, but I think it will be an interesting way to spread, to improve the importance of our discussion and the importance of our work. So as a welcome of the ASIS president, I can say welcome and enjoy this wonderful conference, and I'm sure that we will spend a very nice time all together, at least virtually. Thank you, Filippo.
So thank you so much to Francesco for the kind introduction. I think now, without speaking too much, we can simply start with the first plenary speech. And it's my pleasure to introduce Professor Guyan Kian. He's professor in China, in Beijing, at the Chinese Academy of Science, in the Department of Mechanical Engineering, and he will give a talk that is entitled Crack Initiation Mechanism and Fine Granular Characteristic in Very High Cycle Fatigue of Additive Manufacturing Aluminum Alloys. So I think Guyan can share the screen, and he can start his presentation without hurry, because we are 5 minutes early with respect to the schedule. So he can introduce himself and he can make his plenary talk. Thank you so much, Guyan.
Thank you very much, Philip. Can you hear me, dear friends?
Yes, everything is working.
Okay, good. So good morning, everyone on your side. And right now, here in my side is afternoon. And yes, good afternoon. And thank you very much for the organizer of this conference for having me here in such very critical time. And here today, my presentation will be on crack initiation mechanism and fine granular characteristic in very high cycle fatigue of additive manufactured aluminum alloy. And this work was collaborated with my colleague, Dr. Mr. Jian, Mr. Sun, and also collaborated with my friend Andrea, David, Professor Hong, and Philip. And in my presentation, I will discuss the following 3 parts. In the first part, I will give some words on additive manufacturing, and especially on fatigue behavior of additive manufacturing alloys. And then I will discuss some words on very high cycle fatigue. And in the second part, I will present some results on very high cycle fatigue property of the additive manufacturing alloys. such as the tensile property and microstructure and the effect of built-in orientation on very high cycle property and the effect of powder sizes. And other words, a statistical model, which is introduced by Andre and David, will be used to perform a uncertainty analysis. And in the last part is a crack initiation mechanism for this alloy. And the last part is the conclusions. So as we all know, we are quite familiar with this additive manufacturing process. It is a layer by layer manufacturing process and is driven by three-dimensional CAD and is based on discrete accumulation principle. And it has a lot of advantages compared to the traditional subtraction process, such as it is a rapid prototyping processes, and it has a short manufacturing time, and it can manufacture and repair components with complex shapes, and also it has a high cost performance, and therefore it is in the last several 20 years, it is widely used in a lot of industries, such as biomedicine, automobile, and aerospace, and other fields. However, there are also some disadvantages concerning the additive manufacturing alloys. One of the main disadvantages is that the fatigue performance of these components is quite weak compared to some other components, because during this solidification of in the SLM, some cracks and some porosity could be come out, and then this is our aim to perform a fatigue analysis for this alloy. And concerning additive manufacturing, there are some scientific problems and also some technological challenges, such as defects. There will be a lot of defects, and also the surface roughnesses of the components could be a problem. And also there will be some residual stress. The microstructure is not uniform, and some new model to predict fatigue life is also needed. And of course, there are also some technological challenges, such as the powder characteristic, processing parameters, and so on. And here, concerning fatigue analysis, here, our colleague collected some databases for these two materials. One is titanium alloy, and the other one is aluminum alloy here. And in these two alloys, and we can see that there are some factors affecting the fatigue behavior of these materials, such as surface treatment, surface roughness, and hot isostatic pressing, and also a comparison of the fatigue behavior for the cast and also for this printed material also compared. And we can see, since there are a lot of these important factors affecting this integrity, so it is necessary to include to study some of the important factors, and also to develop some models to predict fatigue life. And so that's the aim of our study, to study fatigue. So why is very high cycle fatigue? Well, very high cycle fatigue means the fatigue loading is beyond 10 to the 7th loading of cycles. This is a new fatigue research area. This can be dated back to 1980s, and it is important because very high cycle fatigue, the mechanism is different from high cycle and low cycle fatigue. Normally the crack usually starts from interior of the crack of the surface. And the other important thing is that now a lot of new engineering components and structures, such as aircraft, engine, and turbine brains, high-speed train, they're subjected to very high cycle fatigue. So the aim of our study is to study the very high cycle fatigue of this aluminum alloy manufactured by SLM, and especially the focus will be on build orientation, printing powder size, and also the crack initiation mechanism, especially on the subsurface crack initiation mechanism will be discussed. And then here, as we mentioned before, here in our analysis, aluminum alloy is studied. The chemical composition of this aluminum alloy is shown in this table. And this aluminum alloy is manufactured in 3 different directions, which is 0 degree build, that means horizontal build, and 90 degree build, and also 45 degree build. Here we show in these 3 figures. And for this specimen here, we can see also the hourglass shape specimen is used for this ultrasonic fatigue test. And the frequency of this machine is 20,000 hertz. And during the test, air will be used to pump to cool the specimen in order to induce the frequency. And this displacement loading is applied, and the stress range is between 40 megapascal and 390 megapascal here. And the right picture shows the specimen for tension test here. And here shows the result for tensile test. Here we can see that the build orientation has a strong effect on the yield stress and ultimate tensile stress and the elongation. Here we can see that the 0 degree build specimen has a higher yield stress and also has a higher ultimate tensile stress here than 45 degree build and also than 90 degree build. And the powder size also has a strong effect on the property. Here we can see that the specimen built with 50 degree microns is higher than that with 20 microns. The reason will be clarified later here. And we know that this additive manufacturing is quite a complex, complex physical and chemistry process. And we know that there's a thermal transfer and mass transfer, and also due to this thermal gradient, a molten pore will be easily formed here because the temperature in the middle of the laser is higher than that in the border, and then this will lead to a non-uniform microstructure will be presented later here. And due to this anisotropic microstructure, the microstructure is observed by optical microscopy from 2 different orientations. Here we can see that. From this direction, here this is a fish scale pattern, which is typically generated by this SLM, and due to this thermal gradient. And in figure B, we can see that there's some molten pore here. We can see that some molten pore, sometimes they are not continuous. This is because the laser is not, sometimes they can penetrate different layers and made it to connect with each other. And also with others, we can also see this non-uniform microstructure. And by scanning electron microscopy, we can further observe the microstructure. We can see the microstructure includes 3 different zones. And here there's a fine zone, heat affected zone, and a coarse zone. And here the microstructure is a kind of cellular microstructure. It includes aluminum and also eutectic silicon is shown here in this structure. And also it is believed that the silicon in the
please, Zoltan, sorry, Zoltan Mayor, can you mute yourself?
Silicon carbide is believed to improve the mechanical property of this material. And also in the fine zone and the coarse zone, we can see the anisotropic microstructure distribution of this material here. And the microstructure is further observed using EBSD here from different orientation, from different angle. We can see that in the direction of building direction, we can see some columnar grains, and this is formed due to the thermal gradient. And in the other direction, we can see this equiaxed grains, which is formed quite uniformly. And also we can see a texture of 001 is formed due to this solidification of this process. And the microstructure is further observed. And here we can see that the both columnar grains and also equiaxial grains were observed. And also we can see some irregular grains and also some defects are shown mostly frequently near the molten pool boundary here, showing this figure. And also we can see some distribution of the grain size of this material here. And of course, the microstructure for the material manufactured with different powder sizes are also observed and also shown in this figure. And it can show the distribution of the defect size, and also you can show the distribution of the grain size. And in general, the defect of the specimen manufactured with 20 microns is larger than those with 50 microns, and also the distribution from the specimen manufactured for different orientations also shown here. And then we come to the very high cycle fatigue property of the specimen manufactured at a different build orientation here. And from this figure, we can see that fatigue strength for the specimen manufactured at 0 degree is larger than that with 90 degrees. This is in agreement with the tensile property, which we showed before. And here we can see that the fatigue strength decreases with mean stresses. This is the mean stress effect. This is also in general with the common practice, and also both surface and subsurface, that is the internal crack initiation, will be shown for these specimens here. And the sphericity and the equivalent diameter of the cracks are also shown here. And we can see that the sphericity of the defects decreases with the equivalent diameter. And most defects are ellipsoid shapes and with equivalent diameter of less than 40 microns. And we can see that the defects of them in this material are also analyzed with the Gumbel distributions. And we show that these two distributions here in these figures. And crack and the fatigue property for the additive manufacturing materials is also compared with those of castings. And the specimen is shown here also in this analysis here. And then one question may arise: what is the reason for the build orientation on the very high cycle fatigue? Why the horizontal build specimen has a higher fatigue and also tensile property than those built with 90-degree orientations here? One reason can be due to the molten pool shape. We know that there are two molten shapes. One is a layer by layer, which is that in different layers, and there will be several layers of this molten pool boundary. And when the molten pool is parallel, they are check by check molten pool. Okay, and we can see when the molten pool boundary is parallel to the loading direction, we can see that then the molten pool will be difficult to slip. On the other hand, when it is vertical to the loading direction, then it will be much easier to slip. And then also, and so in this sense, for the horizontal orientation specimen, then it will be much difficult to slip, and it takes more energy, and then the strength and the fatigue strength will be increased. On the other hand, for the vertical specimen, then the fatigue strength is lower. And to be more specific, and this figure shows the slip in the molten pool boundary. Here, when the loading is vertical, here we can see then the molten pool will be much easier to slip. And on the other hand, when the loading direction is horizontal, and then it will be much difficult to slip. and will lead to higher strength and lower ductility. This is the one interpretation of the effect of building orientation. And the other interpretation of the effect of build orientation will be from the stress concentration effect. Here, for the zero build specimen and for the both 90-degree build specimen, here we can see that they show different morphology, and here the stress concentration is different, and we calculated the stress concentration factor, and we demonstrate the difference between them. And here we see that for this 90-degree build specimen, the stress concentration factor will be much higher than those with horizontally built. And this also explains the effect of building orientation on fatigue and also on tensile strengths. And in addition, the effect of printing powder sizes on very high cycle fatigue behavior is also studied. And from this analysis, we can see that the fatigue strength with 50 microns of powder sizes is larger than those with 20 microns. And the reason could be that the larger surface area of the finer particles lead to more water solution, and the solution conjuncted with hydrogen formation, which may cause high porosity and level, and which may decrease the fatigue strength. And also, fine particles will have worse powder fluidity, which results in higher porosity. And these are two explanations for the effect of printing powder sizes. And in addition, we also observe crack initiation using stress in scanning electron microscopy. And here, 5 types of crack initiation modes are classified. One is crack initiated from surface. And here, you can see that may be due to surface roughness or some other surface crack initiated from surface. And also, crack may start from subsurface and the internal crack, and the lack of fusions and the pores here shows in these figures. And also crack initiated from this internal crack, and it finally grows and form a fish-eye patterns, which shows in figure C. And also we can see that the crack may start from the molten pore, shows in figure E, and also several cracks, multiple cracks also could be found in these figures as shown here in figure E. And this kind of crack initiation modes are somewhat different from those in traditional manufacturing specimens. And fracture mechanics analysis will be used to study crack initiation and propagation. And here we started crack initiation, calculated the threshold of stress intensity factor magnitude. And here we can see that the threshold of the crack initiation is quite constant, and is corresponding to the threshold of the material, while the propagation in the propagation area zone and the threshold, the stress intensity factor increases with the crack area, and this means that the mean stress may play a role in crack propagations. And in order to study fatigue strength, the Murakami model will be used. And the Murakami model, this is also a traditional and is a quite widely used model to predict fatigue strength. And it correlates fatigue strength with Wicker's hardness, the square area of the defects, and the stress ratio. And here, for both surface and internal crack fatigue strengths, the Murakami model predicts quite well. With the result shows good agreement with the experimental results. And in addition, statistical model developed by our collaborator, Andre, and also David, is also used to perform a statistical analysis of the SN curve. And it assumes that the fatigue life follows a log-normal distribution, and here from surface to subsurface crack initiation, and there will be a transition, and there will be two curves, and then these two curves can be modeled, and by assume that the mean value of the fatigue life follows a log-normal distribution, and is also a function of defects in the specimen, and the defects of the specimen is assumed to follow a Gumbel distributions, and then once we got the distribution of the defects, and the fatigue analysis will be done. And here, and then the specimen, and I assume that there's a monotonic linear decreasing model for this fatigue analysis, and then this PSN curve will be analyzed, and the different failure probability, the SN curve is clarified here, and also if we consider two failure modes separated by transition stress, and then a stepwise SN curve is shown here in this figure, and here. And then we can also clarify the different failure probabilities from these SN curves. And using this method, the PSN curve, and also the we can also estimate the fatigue strength at when the fatigue life equals to 10 to the 9th loading of cycles. And here we can see that here we can see the distribution of the fatigue strength for the two printing pod sizes here. And also with this method, we can also see that we can also obtain the result of fatigue cumulative failure probability with fatigue strength. And we can see that with fatigue strength increases, the failure probability also increases. This is also in agreement with our common practice. And then in the next part, we will discuss crack initiation mechanism. As we know that crack initiation in very high cycle fatigue normally start from internal cracks, and also will form FGA morphology here. And what is the mechanism of FGA? And here there are some discussions here. And one reason is assumed to hydrogen, and also there are some other models. And according to my colleague, Professor Hong, it assumes that there's a numerous compressive loading, and this kind of model is now widely used in traditional manufactured materials. However, for these additive manufactured materials, what is the mechanism, and what is the grain refinement mechanism in very high cycle fatigue? And then we comes to this crack initiation mechanism. And according to this numerous cyclic pressing model, it assumes that the crack initiates, and then crack contact, and the compressive stress due to the cyclic loading, and will make after some amounts of loadings will make the grain refinement. And this is now already validated by some experimental observations. And here in our analysis, also for this additive manufacturing analysis, we can also observe some nanograin size in this crack tip and in the within fish eye, within this FGA area here, we show here in our analysis. And we can also see that the crack initiated and mainly propagated along this melting pool boundary, and finally goes to the failure. And in order to validate the contact stress, and here we also use our model to study the contact stress between these two crack surfaces during high cycle fatigue. And here we use this, we assume this plasticity induced crack closure, and we assume that the nonlinear hardening material will be used to model this Bollinger effect, and also used to for building the nonlinear effect of the constitutive modeling here. And then using this model, we start several cycles, and also we try to analyze the context stress, and we can see that the context stress in the crack surfaces, it will increase with the decrease of stress ratios. And the context stress is also quite a high context stress is may lead to the grain refinement, and this is partly validate the NCP model, that is the effect of context stress to make the grain size refinement. And in addition, the internal crack induced crack is also observed here in the in this analysis is also shown by SEM, and also here at a different section, and the cracks, we found some different cracks, secondary cracks, and also statistical analysis, and they are listed in table 1. And here later on we will do some analysis on table 1. And here then figure 1 shows the typical very high cycle fatigue cracks, and we can see that the deep crack 2 deflected at the pore. And in addition, we can see that both these figures, they are intergranular cracking, and they are from modern pore here shown in figure C and D. And there are also defect, there are also transgranular cracking occurred initially perpendicular to the loading direction, and then it will transfer to intergranular cracking in the modern pore, and also lead to 45 degrees directions here. And here in figure 1, we show 2 defects near the modern pore boundary. And we can see that from figure B, a number of new fine grainments will appear between the crack surfaces. And we can see the crack from figure 1, crack 4 was observed and passed through modern pore boundary. And also it indicates that the grain refinement behavior at the crack surface is more evident near modern pore boundary. And also, here in this, yeah. And also in this pore, we shows that also some columnar grains also around the cracks. It shows the fine grains has a higher local distribution in the marked area. And crack 8 is a mixed model of transgranular and intergranular cracking due to the local stress distributions. And here in this slide, the symmetry factor for 111 and 110 slip system corresponding to the area under tension around this area was calculated. And here from this analysis, we can see that the grains through which the crack passes are numbered, and the slip traces of the correspondence are identified. And we can see that the crack path is approximately aligned perpendicular to the stress axis and the defects at applied grain boundaries. And fatigue cracks also propagated towards the void in the material, which implied that defects play a significant role in the fatigue and the fracture behavior of the AM materials here. And the grain refinements in very high cycle fatigue is also a new angle boundary formation mechanisms. And here the misorientation angle and between fine grains and then matrix is also analyzed. And here we can see there exists certain misorientation between the fine grains and the matrix grains. And therefore it is reasonable to believe that it will exist a certain misorientation. And then the angle of this misorientation tends to be 40, 45 and between and 50 degrees. And for the grain refinement in very high cycle fatigue, and here the characteristic and of this grain refinement is also studied, and also crack passing through the molten pool boundary, and also crack inside the improvement boundary also studied. And this is a grain refinement is a new angle boundary formation phenomenon based on the numerous cyclic pressing, and the growth of crack along grain boundary leads to the diffraction of crack propagations path and roughness of the crack face. The local crack diffraction promotes grain refinement out numerous cyclic pressing in very high cycle fatigue. Here shows in this study here. And the fracture surface felt in about 10 to the 9th loading of cycles is also observed by SEM, and also this specimen is also further observed by TEM and the TKD. And the figure in the right field shows that there's a fine-grained layer near the crack surface, and also significant misorientation was also observed in the fine grains, and it also indicated that the activation of this location is the result of coordinated plastic deformation, and also dislocation activations from subgrain boundaries will lead to misorientation, and as plastic deformation accumulates, dislocation piles up, causes the formation of a large angle grain boundaries. This shows the crack initiation mechanism, also as well as the formation of fine granular area in the very high cycle fatigue. So from what we started before, the following conclusions are drawn. So firstly, the build orientation has a great effect on mechanism and properties, mechanical property and fatigue property of this additive manufacturing alloys, and the horizontal manufacturing specimen has a higher strength than 90-degree manufacturing specimen, and 50 microns printing powder size lead to a higher fatigue strength than those of 20 microns. And 5 different kinds of crack initiation modes are identified, and the statistical model is used to perform SM-PSM study. And as a result of heterogeneous microstructure, the intergranular cracking induced by incomplete fusion defects is a dominant failure modes. And also we also stress that numerous NCP, numerous cyclic pressing model is a dominant model to induce grain definement. And also heterogeneous distribution of fine refined grains underneath the crack surface is strongly related to printed microstructure and the crack propagation path. And with those, thank you very much. And thank you again.
So thank you so much, Guyan, for the excellent presentation. We have time for some questions from the audience. I think there will be some questions from the audience. Don't be shy, and if you want to ask curiosity about the presentation, you are welcome now. So I'm involved in the work, so but still I can ask a question to the plenary speaker. Yeah. So I would like to know which is the future work that you consider important in this field, and which are the next the next investigations that you consider important to better understand the phenomena that you have described now.
I think in a first step, in order to better understand the formation of fine granular area, and still a lot of experiment and better observation of the microstructure is still needed. We need to quantify the size of grain size of these nanograins, and also we need to know the orientation, the distribution of these nanograins. And in order to do so, we will need some advanced tools. We will need different observation methods. This is one direction. And in addition, we also need to develop some good tools to predict fatigue life, and also especially to predict the correct initiation and the correct propagation time, lifetime of this material. And since this is this kind of material is somehow is different from the traditional materials, so the old method, whether the old method could be still be valid for this new material, then I think there will be some kind of a question. Maybe we need to further develop. Maybe we will develop some new methods considering this microstructure of this material. Yeah. I think this will be another direction. And thirdly, since the microstructure of this additive manufacturing is a kind of heterogeneous distribution, and we can also get some inspiration from this process. Maybe by using this new process, we can, in the future, we can manufacture some, we can change the microstructure, and then therefore we can manufacture some materials which has not only the higher strength, but also the higher toughness, also ductility. So in this sense, we can manufacture better materials. That's all. Hope.
Yeah, thank you so much. There are also three people that raised the hand. So the first one is Professor Gianni Nicoletro from University of Parma. So he can make his question now.
Okay, thank you. Can you hear me?
Yes, yes.
Okay, fine. Thank you for your presentation. I have a couple of questions related to the fabrication phase of your material. You mentioned, or you refer to powder size 50 microns and or powder size 20 microns. Actually, normally there should be some kind of distribution, and I imagine that those are average values of the grain size. So maybe you have distributions as well. I think in the width of the distribution, I think it's quite important for the understanding of the role of powder characteristics on the material properties. You don't mention, on the other hand, the layer thickness that has been used to produce these specimens. Do you have a specific layer thickness that have been used, or that has been decided or defined? And
yes.
Third, maybe I can add the last question, and so you can answer to the questions all in the same time. What about any post-fabrication heat treatment? Do you apply any post-fabrication heat treatment, or you test it in the as-built condition? Thank you.
Oh, thank you very much for your very detailed question. Yes, and indeed, yes, the distribution of the powder size follows a Gaussian distribution. And here we mentioned these two sizes, they are the mean value. So that means the mean value are this, and this is the first one. And for this layer thickness here, actually we did not mention, and in our analysis, the layer thickness is about 150 thickness microns in this analysis here. And I hope I will add it in my presentation. And for the heat treatment, in the present, here in the result I showed here, they are not, they have not gone any subjected to any treatment. But as a comparison here later on, we also did some heat treatment, and this result will be maybe presented in the next conference, and also will be published recently. And also we changed the heat treatment, and we also performed isostatic pressing, and we will compare this effect or the processing parameters on the fatigue behavior, and especially on very high cycle fatigue behavior. Thank you.
Yes, thank you so much. There is a question from Professor Jürgen Stampfel from TU Vienna.
Yeah.
Yes, so we can ask him to make the question.
Yeah. Hello, and thanks for this interesting presentation. According to your results, it seems that the defects are most critical. Do you see ways to modify the process in order to reduce such defects? So meaning
Yes.
changing parameters or modifying the SLM process in order to get rid of some of those defects?
Yes. Yes, especially in very high cycle fatigue, because when the loading cycle is longer, and then there's a defects plays more critical effect on the fatigue behavior, because in very high cycle fatigue, and the small cracks and also some cracks in the interior of the material will function. And in this sense, some small cracks in the internal, and also the porosity, lack of fusions, they will start to initiate, and even multiple cracks, they will initiate simultaneously, and will lead to coalescence and lead to the failure. That's our experimental observations. So I totally agree with you that the cracks are very important, are very critical in the very high cycle fatigue behavior.
Well, thank you so much. There was another question from a person that I don't see anymore. But,
my question was
yes,
actually
yes,
answered.
yes.
Yeah, my question was answered.
Okay, perfect. And after that, there are two questions in the chat. Did you have any issue with residual stress? And did you detect any influence of loading intensity in the type of defect at 0 or 90 degrees? So these are two questions.
So the first question, the residual stress, right now have not yet studied the effect of residual stress. And in this is also our future work to study the residual stress, as you just mentioned, Philip. So in our future work, so the residual stress, I think we found some good tools using this crystal plasticity. We may somehow introduce some residual stress distributed in the grain size, and we try to analyze this residual stress. This is the first question. And the second one.
And the second is, did you detect any influence of loading intensity in the type detected 0 or 90 degrees? Probably Professor Luis Reis can also make the question alive if he wants, because it's not really clear what he means.
Loading intensity in the
yes.
Yeah.
Yes.
Hi, good morning, Filippo.
Yes. Go ahead.
Professor.
You're welcome.
Thank you for your very interesting presentation. Yeah, I mean, if you have detected any influence of the loading intensity, because it's related with the power that you have to deliver in your experiments. So if you have any type of influence in the geometry of the defects in 0 or at 90 degrees. That's clear?
Yes. I think right now we have not yet studied this loading intensity for these two defects. But we tried to analyze the stress intensity factor. I'm not sure. I think that there are two different issues, not the stress intensity factor for these defects. So we used the methods. We also used the Murakami's models to study the stress intensity factor for the cracks for the different orientations. We used the Murakami model, and we also used calculated stress intensity factors, and that's what we did. And in addition, we also, for these defects at a different orientation, we also use the Gumbel distribution to statistically study the distribution of the cracks, and we found the difference. Also, the Gumbel distribution, which is assumed the crack follows the least extreme distributions, which is also a kind of a method to statistically study modeling the distribution of cracks.
Okay.
So-
Okay.
I'm not sure.
Was clear. Thank you very much.
Thank you.
Thank you so much. I think we are perfectly according to the schedule. So now we have 20 minutes of break. We thank again Guy and Kian for the excellent presentation. And we have now 2 parallel sections that are starting at 10:20. So we will rejoin the 2 parallel sections at 10:20. You can find the 2 sections in the program. So we will meet again in 20 minutes. So thank you so much again,
Thank you.
Guy. Thank you.
Thank you, Philip.
Thank you.
Thank you
Thank you.
all.
Thank you.
Thank you. See you around. See you. Bye.
Hello, everyone. My name is Javad Razavi, Associate Professor at Norwegian University of Science and Technology. We have the first session of today, session 1.1. And we will start with the first presentation. Of course, the presentations would be kept shortly to have sufficient time to hear the questions from the audience. The first presentation is by Mr. Chen. The topic is selective electron beam melted non-weldable nickel-based superalloy. Mr. Chen. If any of the authors from the first work are present, can you please reply? Okay, they're apparently not present. We can have that presentation at the end if the authors are back in the room. The second presentation is presented by Claire Gong. The topic is 2D characterization of sub-micron scale of crack propagation in 17 for precipitate hardened part produced by atomic diffusion additive manufacturing process. Is any of the authors present from that work?
Yes.
Yes.
Yes. Can you hear me?
Yes.
Okay.
Please.
Hello, everyone.
Yeah.
Yeah, so do I have to do a 1 minute presentation, quick presentation of my study? Is that right?
Yes, please. Yes.
Okay. Okay, so as the title said, the study is focusing on a new method, which is the nano gauges gratings deposited at the surface of 2 single-edge notched specimens thanks to the electron beam lithography process. And then we do an in situ tensile test under SEM in order to observe the crack initiation and propagation of a smatted sample and an as fabricated sample through the atomic diffusion additive manufacturing made with, the atomic diffusion additive manufacturing. And the different results that we got indicate a difference in the number of cracks. So the SMAT one has less cracks than the as fabricated sample. And we can also see a difference in the stress at which we have the first cracks. So if you have any questions about this study or from the video.
Thank you for your presentation. From the audience, is there any question on the presentation of Ms. Gong?
Yes, I have just maybe a small question. It's more on the like in your 2D characterization, you did some the nano gauge gratings. Can you explain a bit how did you do it? How did you put these? How did you make this in the sample? Did you use FIB? Did you use what technique did you use to do it?
Do you mean what is the process for depositing these gratings at the surface, right?
Yes, exactly. Thank
okay.
you.
No, it's okay. So the process is through the electron beam lithography. So after preparing the surface of our specimens, we deposit a layer of resin at the top of the surface where we want to put the gratings. And then we put them in a specific MEB, in the specific SEM, where an electron beam will remove some parts of the resin. And then we apply a thin layer of gold at the top of this resin, but also on the surface, on the sampled surface. And then with a solvent, we remove resin, which also has at the top of it the gold layer, and at the end we only have the some gold nanoparticles at the top of the surface. So
yeah, okay. But did you and then did you do some DIC afterwards on your results, or did you because I see that you're tracking the cracks and everything,
yes.
but like because I assume that you're using this to some type of tracking or to be able to correlate the
yes, absolutely, yes. The principle behind this method is quite the same as the DIC. I agree with it, except that the DIC, it is based on the fact that we have some random patterns instead of a regular one. So it's easier for it to follow the evolution at a certain scale. But for this method, the main objective is to have a more precise following of the cracks initiation, for example. So which is why it's a very precise deposition. It's a very small one too. But yeah, the principle is the same. It's quite the same as the DIC, except that we want to track the centers of the nanoparticles.
Okay. Yeah. No. It looks very similar to the grid method as well. I don't know if you're familiar with it, but it's definitely very interesting. Thanks.
Any other questions from the audience? I actually have a question. So these techniques, similar to this, what we were doing before was to use indentation to create this pattern, and it was quite demanding and also locally damaging the material. So it was quite nice to see the results that you presented in your work. What I'm wondering is, what is the maximum surface roughness range approximately that you can apply this technique on?
Well, for this study, we smattered we smattered a surface. I think the roughness is bigger than what it was applied before. The roughness, if I remember, it's like 400 micron from a arithmetical roughness, if it's the word in English, sorry. So yeah, it's bigger than what we can see in the ABL process normally, but it was we got some pretty good results, and we can exploit this. So it's a very satisfying results.
Thank you very much for your presentation.
Sorry, it was 400 nanometers. Sorry, it was 0.4 micrometers.
Okay. Yeah.
Sorry.
Perfect. Thank you very much.
Thank you.
We can move on to the next presentation. The title of the presentation is A First Step in the Development of Dense Metallic Architectured Materials by Additive Manufacturing. Presented by Mr. Florent Hanard.
Yes. Hello. Can you hear me?
Yes. Please, if you can shortly present your work.
Maybe I can just share this one slide if it's
absolutely.
Okay. Okay, so the goal of this topic is to develop bio-inspired dense architectured metallic materials, and hopefully with high toughness. And here, architectured means that it's really like a regular pattern made of well-organized periodic configuration of constituents with very different natures, such as, for example, defect-free zone or defects which are forming a weaker interface. And here, dense means that it's really only a few % of porosity. It's really not like a lattice or such things that usually people are talking about when using the word architectured materials. And so the idea is to organizing the defects associated with the LPBF process in such a way to organize them in interfaces, and this will generate hopefully a mechanism of improving the toughness, such as crack deflection, inhomogeneity effect, and so on. And so the idea, this might seem counterintuitive, but here the idea is really to go in the other direction. So usually people try to fight defects, and here it's the opposite direction. The idea is to try to control the generation of these defects as well as possible, and to organize them in such a way that we can actually improve the toughness of the material. And so in my presentation, I've shown preliminary results obtained in TI6L4V printed by LPBF. And if you have any questions, please feel free to ask.
Thank you, Mr. Hanna. From the audience, is there any question on this presentation?
Yes, I have a question.
Yes, please.
So first, thank you very much for this presentation. It was very interesting to listen to and to watch.
Thank you.
I just have a question. I don't know if you mentioned it in your video, and I'm sorry if you did. I just want to know, what type of material did you use for this study?
Yeah, so in this case, we use TI6L4V, so the classical composition. But actually, at least for this strategy, so in my talk, I talk about different strategies that could be used to generate interfaces. But if we use defects, such as generated by Keogh mechanism, this would not be, I mean, in this case, we use titanium alloys, but this could potentially be applied to multiple type of materials. And that's also one of the interesting point about this strategy, is that it's more focused, for example, here on a printing strategy than really optimizing the composition of the material.
Okay, you just answered my second question. Is I just want to know if it was if we can apply it to other materials. So you answered it already. But I also want to know if this method can be applied to other process, because I think you did it for powder bed based process. Can it be applied to other method, for example?
Yeah, well, I mean, from a general point of view, you can, any process, even going out of additive manufacturing and metals, any process, any manufacturing process in which you have so the key point in architecture materials is to have a fine control of the local properties. So in additive manufacturing, of course, you can play with the laser parameters, which allows you to change the microstructure locally. But any processing parameter in which, any process in which you can control locally the properties of the material, if you can generate like a strong contrast between the properties of the different materials, you can generate an architecture materials. And that's actually what has been done a lot. So I'm trying to apply this strategy in metals, but this strategy has been applied in many materials, most famously, for example, in glass or ceramics, which is very brittle, and you can use polymers in between that will sustain a very high ductility, improving a lot the toughness of the material. So yes, definitely you can generate this concept to any process that allows you to control the local properties.
Okay, thank you.
Thanks a lot.
Actually, after watching your presentation, it was quite interesting for me. We have also worked in a little bit easier cases, trying to redirect the crack path and eventually changing the fatigue failure mode from a mode 1 to a shear mode. So increasing the fatigue life. Of course, it was an architecture structure. It was just defining some alternative path for the crack to propagate. And it was really nice and pleasing to see the results that you have obtained. I only have one main question. So your presentation was mainly oriented toward fracture toughness.
Indeed.
And when you're statically loading a metal, of course, you have some aspects that you will deal with, like plastic deformation. You may get higher toughness from this material, but what do you think the properties would be if you have acyclic loading, when you have defined these defects in the material?
Yeah, that's a good question. So first of all, I would be interested to see the work you mentioned at the beginning of your question. That's for sure an important question. So of course, we already know that in some application, the toughness is really the primary properties to improve. But indeed, there is also the question of fatigue. And you could think that if you increase the amount of porosity, obviously you will decrease the properties in fatigue. But then if you watch the video, you also have seen that I'm working on different strategies. So not only using porosities, but also, for example, using a dilution effect in such a way that we, for example, control the amount of molybdenum that goes into a titanium matrix. And so for this strategy, only based on, so to be clear, I started with this one, controlling the defects, because it's the easiest one and it's kind of a proof of concept, at least for toughness. But definitely, if this is working and giving good results, when actually no, I'm doing at the moment fracture testing, and if this is giving promising results, then definitely with the other properties, we will also look at fatigue. But I cannot really tell in advance. What I'm hoping is that maybe the segmentation of the material into cells could, of course, maybe you will increase the amount of micro cracks nucleations because you increase the amount of defects, but maybe you could also somehow confine its propagation. So these structures are very different from the monolithic materials. So maybe we cannot just think of the mechanism that will happen just by directly looking at materials with a low amount of defects, and maybe we'll see something very different. But I'm really not an expert in fatigue, so if you have any feedback, maybe you can contact me also after, and I would be very interested to see the work you've been doing.
Yeah, for sure. Thank you very much for your presentation.
Thank you.
So time is a little bit limited. We can move on to the next presentation. The title of next presentation is Tough and Damage Tolerant Composites for Biaxial Loading, presented by Drazen Breskovic, if I pronounce it correctly.
Yeah, that was quite good, yeah.
Please, if you can give us a short intro to your work.
Of course, yeah. So basically, we developed a numerical model based on the configurational force concept and on a ductile-based approach to investigate inhomogeneities which are suitable for designing biaxial composites. In former works, we have mainly focused on composite materials which can only be loaded for under uniaxial loading. But to extend the usage of composite materials even to multi-axial loading, we have now focused on like isolated inhomogeneities, which are, in our example, holes, for example, to improve the fracture toughness of materials. So in this case, as if for the one-dimensional case, for example, the crack path was not an issue because the crack path always has a unique propagation direction. In our case, if you have isolated inhomogeneities, the crack path becomes very important. So we focused on isolated inhomogeneities like holes to attract and arrest cracks so that we can then improve the fracture toughness of materials. So we developed a numerical model, which is even set and based on the configuration force concept, to find a method, a quick method. It was important to investigate how strong a hole can attract a crack under different loading conditions, for example, and how much will, and in the second step, even how with a ductile based approach, how much improvement do we gain to arresting cracks in a quite brittle material. And the outcome was like, even with, for example, with a secondary defect, if, for example, if our hole isn't perfect, we gain in our calculations, we have seen that, for example, a 10 times higher fracture toughness can be achieved by arresting cracks with holes, for example. So that was just a short overview.
Thank
so
you.
Yeah.
From the audience on this presentation, is there any question? Okay, I have one question. So this technique that you have used for composite materials is actually quite nice, and traditionally it was used previously for metallic material for both cases of static and fatigue loading. Mm-hmm. And in the case of fatigue, of course, it was the fatigue life for the crack to reach the hole, and then the initiation life for the crack to get out of the hole. But that hole was something that we purposely introduced, called a stop drill hole, to stop the crack. In your study, you were mainly focused on presence of one of these defects. If you have a multiple defect case, let's say, for example, the composite material that you have is fabricated with FDM technique. So you have a tabular presence of these defects in your material. How would you implement these multiple defects in the material when you're using the procedure that you already used?
Thank you for your question. Yeah, we already did this. That will be, for example, presented in some future works. The advantage of this work is to we can calculate the crack path, for example, for 1,000 of paths in several minutes on a normal workstation. So it is very easy adaptable to a range of multiple areas of holes, to find really the right geometry in a composite material to arrest as much holes, cracks as possible. It's because the method we used is an interpolation procedure. And for example, we in our case used a superposition procedure to just adopt as many holes as we want to see if we get, for example, the most toughness of the material and as much stiffness as possible.
Do you think it would be possible to also capture crack branching? Because in materials such as composite materials, we have these crack branching. So you don't deal usually with one single crack plane, and it can branch into two or even more. The material is quite brittle. So, but would it be possible to somehow insert in your model also that part?
Of course, as I just quick thinking over it, yeah, if we have, for example, criteria to start crack branching, and then from that point on proceed as with one crack tip, just with two, so tracking not one crack tip, then there's two or three or as many as we want to the material would be not a problem, I think, with this procedure.
And the last question, for propagation, for example, in this crack that you mentioned, if, for example, considering a crack that has two crack tips, mm-hmm. Will you apply a constant growth step for propagating these cracks, or how is it? Just very shortly, I know this is some future work you're thinking, but just to get your opinion.
In this case that we presented, the incremental crack extension was constant, but for example, for fatigue loading, where the crack propagates into a region where the crack driving force increases, it is absolutely possible to link the crack extension to the crack driving force at this particular point, and then to maybe estimate the lifetime, the fatigue lifetime of a crack in an assembly of holes, for example.
Thank you. Thank you for your response.
Thank you very much.
We still have some time. Any question from the audience on this presentation? Okay, good. We can move on to the next presentation. The title is Analysis of the Behavior of Lattice Structures under Low Velocity Impacts, Simulations and Experimental Tests, presented by Andrea Tridello.
Hi, Javad. I'm Davide Paulino. I will substitute Andrea since he had an unexpected commitment, and so I will present as a co-author. I will just share a brief presentation if I can. Can you see it?
Yes.
Okay. Let me add. Okay, the work is about the analysis of the experimental and numerical behavior of lattice structures manufactured through AM processes. And the aim of the work was just to select the best performing lattice cell among 5 possible structures, and then to implement an efficient numerical model to predict the behavior under compression, quasi-static tests, and also impact tests. The first validation and numerical prediction was performed with carbon nylon material produced through this. Sorry, I didn't remember to go on. Produced with this Ultimaker testing equipment. Manufacturing equipment, and then we run quasi-static compression tests and also numerical models, and we got that the best choice for the lattice cell was the lattice cell number 4. The prediction with numerical models was quite good and also efficient, since we very simplified the model by using 1D elements and an elastoplastic behavior. And we got a very good agreement between the quasi-static compression tests on the cell and the numerical model. As for the force displacement curve and for the failure modes as visible in this slide. Then we decided to implement the cell structure with an ALSI-10 alloy made through SLM. And indeed, we have to slightly modify the model to add another constraint to the failure mode to have an acceptable agreement between numerical and experimental behavior under quasi-static compression tests. Then we ran impact tests on ALSI-10 specimens, and we found that a significant strain rate effect was present, and this had to be also modeled to rightly predict the maximum impact absorbed energy. Indeed, the final results were quite good in terms of final values of absorbed energy, but the shape of the curves is not so in agreement. This is why further development are necessary for the model to rightly predict what happens with ALCY-10 alloys, metallic alloys. And this is the further development. To conclude, I think that what I said is already present in the conclusion. Thank you.
Thank you for presenting your interesting work. From the audience, does anyone have any question on the research that was presented? I actually have one question. The work was really nice, and also the part that you showed the verification of your numerical simulation, it was quite nice and quite matching. Yeah, in this one. I was wondering, for the mechanical properties that you put as input in your model, how were they calculated?
Yeah, we indeed ran quasi-static tensile tests on specimens in carbon nylon, and we got the stress strain curves, and then we implemented the real curve, the actual curve in the model, so that it's a specific model for that carbon nylon specimen and material. This is, in our opinion, was the best way to catch the complete behavior. And indeed, we didn't model the anisotropic behavior of the carbon nylon, but indeed we got good results in terms of modeling. This is why we didn't get too much into the detail in modeling the material behavior.
Yeah, usually when fabrication is done properly with good infill, anisotropy is quite limited,
yeah,
in different directions and printed with FDM. How about the dimension of the specimen that you tested? Because these lattice features are quite small.
Yeah, I just go back to this slide. The unit cell was, the specimen geometry was 9 millimeters, and 3 cells were superposed to have this specimen. The beam diameter, the struct, so is 1.5 millimeter. These are the dimension used. And indeed, even with such small specimen, the computational time required with this very simplified model was about 10 minutes. If we also tried to run 3D elements model, and it took more than 3 hours. Obviously, it depends on the machine that you are using. But with a commercial laptop, these were the computational times.
But by dimension, I mainly meant the tensile.
So I cannot hear you. Sorry.
The dimensions of the tensile specimen that was used to capture the material.
Well, I think I didn't run the test, and I don't remember. You can directly ask to Andrea, but I believe that every time we run tensile test according to standards, and I believe that this was according to the ASTM standard. So it's there indeed. I can comment about this. I don't know if it was a macro scale specimen or not, but I believe yes. And indeed, you can think about a size effect between lattice structures and specimen under test. And my feeling, according to the results that we got, is that even this effect was, let's say, hindered by some other aspect, and in the final element model, finite element model, the agreement was quite good.
Okay, yeah. And the last question.
Yes.
How about the material properties when it comes to the rate dependency? Did you perform any more testing to get the material properties, or was
yeah,
it
no, well, we ran free tests at free velocity, 2 repetition each for each velocity, and we put in the model, in the Johnson-Cook model, the values that we got with these free values of velocity, and finally we got something which was in quite good agreement in terms of absorbed energy, but indeed the part related to the aluminum alloys has to be developed a lot, since I cannot tell you we got good results in terms of modeling.
Okay. So for material property, you repeated the tensile testing, but with different weights. Okay.
Yeah.
Perfect. Thank you so much.
You're welcome.
We still have time if there is another question from the audience. Okay. Thank you again, Davide.
Thank you, Javad.
We can move on to the next presentation.
Let me stop sharing. Okay.
Yeah. The title for the next presentation is Fatigue Assessment of Laser Beam Welds between ALSI-10Mg, is aluminum alloy, structure and conventionally manufactured aluminum by local approaches. The research is presented by Mr. Benjamin Moller.
Yes, good morning, everybody. I also prepared one condensed slide, which I might like to share. So if you can see my screen now. So this work is, starting from the question or answering the question, trying to answer the question, what happens if we join additively manufactured materials, so in this case, aluminum, silicon, tin, magnesium, with conventional materials, aluminum materials, which we might use in the case of larger structures for the automotive industry, for example. So therefore we set up an experimental and numerical test program using lab joints, which are laser beam welded between additively manufactured material here in the upper part and conventionally manufactured aluminum 6082 in the lower part, had a test program with fillet welds and welds which run through the two materials. And in the first step, just evaluating nominal stresses in this case. And what we found is that for these fillet welds, we have seen that the recommendations fit quite well. For this case, it's FAT 12, which has to be applied. And we have seen also that the porosity in this weld increases, especially in the area where we have the additively manufactured material. So these are two main points coming from the experimental work, and then we started to try to develop local methods for assessing these joints. And what we see here in the notch stress diagram versus cycles to rupture is the outcome of the numerical simulation of these welds, and especially we see that these fillet welds, which we see here in the numerical model, which have the fatigue failure starting from the weld toe, the black symbols are here in good agreement with the gray circles from previous investigations on conventionally manufactured aluminum welds, while these run through I-shape laser beam welds are in the in the lower part of the SN curve and do not really fulfill these recommendations. So yeah, there is still some work to improve this process on the one hand side, or to include, for example, defect porosity into the notch stress approach. In a second step, there was a so-called battery carrier, which is used in the automotive industry for electric cars, for example, as a component where additively manufactured connection nodes are welded to conventionally aluminum sections, and this was tested under also biaxial loading conditions comparable to the application. And in these investigations, experimental investigations, we could see that we also find cracks at least in 3 out of 7 experiments, which are running through the laser beam welded seams, and therefore cause failure of these more or less complex structures. From the numerical point of view, we see that notch stress approach is not applicable due to these full size models, so that a structural stress approach has to be chosen, which was in good agreement in this case for the whole battery carrier to estimate the fatigue life of such a weld seam. Yeah, this is more or less so the outcome of the work, and I think there is still some work to do. So thank you, and yeah, I'm open for questions.
Thank you for your presentation. It indeed has been a topic of research lately about welding of these complex that we fabricate with AM to the conventional part, because usually we don't need to fabricate the whole part or the whole component by AM. So it was quite interesting to see your finding. Let's see from the audience, there is any question? Okay, I have 2 questions. Okay. Mainly. One is about the defects that you saw, the internal porosity. In the presentation, you mentioned that this, and also it was shown that these defects are more in the welded area closer to AM part. And as the cause, you mentioned that it's because of the remelting of AM side of the joint. Why do you think these large defects are created when the AM part is being melted, but not when the conventional part is melted? Exactly.
Yeah, we did a little study on this, trying to decrease the large pores and the porosity in this area by preparation of the sheets in advance of welding, by etching, mechanical removement, in order to try to get rid of the oxides which might come from the outside. But obviously this was not the main reason why we've seen, or why we see here this porosity, so that it has to be, from our point of view, the reason has to be inside the AM material, so that we think the porosity which already exists in the AM material due to the additional heat input causes these extension of pores and porosity.
Yeah, so I didn't quite see chemical content for these 2 alloys that were welded. I don't think they were exactly the same, but could it be that the welding process parameters is not well optimized for the AM side, but perfectly optimized for the conventional side?
Yes, for sure. This might be a next point to investigate, since there is not much experience on welding of AL Si10mg. It's some experience from casted AL Si10mg, but not so much compared to the conventional one, for sure. So that the first starting point was to use parameters which fit to the conventionally one. Yes.
Okay. We got a question from Mr. Sprengel. He has asked, what happens if you flip around the stacking sequence? Let's say you have done the welding with the AM part on the top, the overlapping part. Does it make any change if you change the sequence?
Yeah, we also made some trials on this, and we have seen that we got more problems, let's say, changing or flipping around this, since also the conventionally 6082 material is not too easy to weld, so that we struggle with this material when we flip it around. So this was the more practical choice in this case. So we have cracks in case if we flip it around, or more tendency to have cracks in the conventional material.
Okay.
Yeah. Thank you.
And
sorry if I interrupt, can I ask a second question?
Yes, please.
After the welding, so first of all, thanks for the presentation. After the welding, the laser beam welding, do you apply any heat treatment on this stacking of the two plates?
No. After the welding, there was no heat treatment. We had a heat treatment in advance for the AM material. It was the stress release heat treatment, and for the conventional one, it was a T6 heat treatment. But afterwards, there was no heat treatment performed. No.
Okay, thanks a lot.
Okay, I'll come back with the second question.
Okay.
You basically pointed out to my question in your short presentation. How do you want to implement the presence of these defects when you are doing theoretical evaluation?
Yeah, that's not an easy solution for it, I think. So we've seen this morning that we can introduce some distributions on these pores to the material. In this case, I don't think it's the right way to include all of these pores in terms of a distribution, since we have fatigue failure starting from the weld toes in case of these fillet welds, or from the weld roots. So it's more about to investigate how the cracks exactly initiate at these points, instead of trying to include this pore distribution somehow to the notch stress approach, or furthermore to the structural stress approach. For the material itself might be a chance, for example, by representative structural elements. There is a talk tomorrow from my colleague Rainer Wagner, who had some approach, or is presenting an approach for it. But in terms of welded joints, I think it might not be the right solution.
As a solution, you can have models which are based on the experimental data on simplified cases, and then add a factor, let's say an increasing factor for the stresses depending on the defects that you have. And that defect size can be obtained, for example, with CT scan. So you don't need to do the testing, and figuring out where on the fatigue plot is your data approximately located. And the last thing is just a comment on the mesh size of the real structure that you did the simulation on. It seemed quite coarse, and for getting the stress values from it, in my opinion, I think you would need a much finer element there, unless if you're using methods that are mesh size independent. For example, the energy techniques. In those cases, you can use quite coarse element to get the energy, strain energy in your part, and then have the prediction based on it. But this is more of a comment. rather than
I totally agree with it. So yes, for sure. For such a structural stress approach, I think there needs to be a procedure. If we use such a coarse mesh, how exactly the stresses have to be evaluated, or on the other hand, the mesh needs to be more refined. And there is some ongoing work actually, which we do. About the influence of the mesh refinement for these hexahedral elements which we place in between the two materials. Yes. Yeah.
Thank you very much for your presentation.
Thank you as well.
Well, we can go ahead and get to the 7th presentation. The title is Cyclic Deformation and Fatigue Behavior of Titanium Alloy Ti64 built by Directed Energy Deposition AM process. The talk is presented by Mr. Abdul Qadar Syed.
Hi, hello, good morning, everyone. Can you hear me clearly, Jawad?
Yes.
Yeah,
please,
thank you very much.
Introduction.
Yeah, okay. Thank you very much for the introduction. Today, I'm going to present strain control fatigue behavior of titanium alloy Ti64 built by wire and arc additive manufacturing process, which is a directed energy deposition AM process. So as you all aware that application of AM built materials in heavily load structural applications is always need to be assessed under cyclic loading conditions. Therefore, we focus this research mainly on to understand the strain control fatigue behavior of warm Ti64 built materials. So this, I'm just showing a summary of the overall research we have conducted. So we have used a wire and arc additive manufacturing process in Ti64 as raw material. And we build these materials using a oscillation build strategy developed for warm process. So basically in this oscillation build strategy, you could actually oscillate your wire and the torch along the wall thickness direction, where the travel direction is along the wall width direction. So we have tested the materials in both horizontal and vertical orientation with respect to the deposition layers. So what we have found is because of the lower heat dissipation associated with these build strategies, we have found a very large or wider primary beta grains ranging from up to 300 to 500 microns in terms of width and few millimeters in terms of their length. And within these primary beta grains, we have found some large microstructure heterogeneity. So majority of the material is composed of either basket weave or colony morphology. However, we have found some alpha grain boundaries where we have some colony microstructure on one side, and other side there is a typical basket weave microstructure. So we can expect that with such microstructure heterogeneity, there will be some influence on the cyclic performance. So on the right-hand side in the middle, you can see the overall strain control fatigue results of warm Ti64 sample, which is in the filled symbols, compared with the literature data, which is in the open symbols. So just for the clarity, I have highlighted the low cycle fatigue regime and the high cycle fatigue regime within this plot. So if we look at the warm Ti64 data, we can see that we can observe the influence of primary beta grains and this microstructure heterogeneity on the overall anisotropic behavior, where vertical samples showed a marginally higher strain control fatigue behavior when the applied strains are within the low cycle fatigue regime. However, we don't see any much difference between the horizontal and the vertical samples when the test data is in the high cycle fatigue regime. And compared to the AM build materials, we have similar properties with compared to lens. and lower properties than SLM. That's mainly due to SLM has Martin-CT fine microstructure. And we have observed that all the samples tested in this program have a crack initiation from the microstructure feature, and we did not find any defects. That is confirming that we able to build a very dense material with a high quality wire. And when we looked at in detail in the crack propagation region, we have found a large secondary cracks, which is a consequence of the colony microstructure that we have observed, because that will lead to formation of secondary cracks, and also changing the mode 1 driving force to sometimes mixed mode 1 and mode 2, and also helping in lowering the overall crack propagation rate and increasing the overall fatigue life. So that's it from my side. Do you have any questions?
Thank you for your presentation. From the audience, if there is any question on this presentation. Okay, I can ask a question. Well, the material was fabricated with the wire arc additive manufacturing, and this technique, same as other AM technique, would result in residual stresses in the component.
Yeah.
I didn't quite find any info regarding the residual stress in the samples that were studied. Obviously, all the mechanical properties that you're observing now is not related to the microstructure. There is a part that is the effect of the residual stress. What is your opinion? What do you think is the state of the residual stress in these horizontal samples and vertical cases, and in which case it can be more dramatic?
Yeah, that's a good question, Jawad. We actually did a parallel program on to understand the residual stress behavior when we actually remove the wall from the substrate, and also after extracting some dog bone samples and also some compact tension coupons for the fatigue crack growth testing. And we have observed that after extracting these sort of very small samples around the diameter of 10 millimeters, compared to the size of the wall, which is 500 millimeter, there are very less residual stresses, which are actually very close to any technique's resolution. For example, we can say around 10-15 megapascals in terms of the overall residual stresses. So I don't think in these builds residual stresses as the main concern, but we have seen when we have extracted the compact tension coupons, obviously we have seen some localized stress concentration at the EDM notches that actually resulted initially marginally higher crack growth rate in those regimes. But however, we are also trying to do some parallel program on applying some stress relieving treatment, and trying to see what is the real impact, whether if there is any impact of residual stresses in the as-built and the stress relief condition, and then we will be sure on that whether we really have any residual stresses impact, or it is purely a microstructure influence on this anisotropy.
Thank you. But looking at the fatigue plot that you have, this results that you're showing, in the case of low cycle fatigue, we are getting slightly better fatigue properties for the case of vertical samples.
Yeah.
While looking at the mechanical properties, the yield strength is not that different.
Yeah.
What do you think is the main source for this variation only in the low cycle fatigue regime?
We have some understanding on this anisotropy behavior, particularly the reason why horizontal samples are showing lower fatigue performance compared to vertical. This is, we currently think that the microstructure heterogeneity along the primary beta grain boundary, which has either colony or the basket weave microstructure, and it is also spatially changing within that gauge length of the sample. So that is one of the source whenever the material is loaded along the horizontal orientation, this primary beta grain boundary is acting as a weaker interface. However, we are parallelly conducting further studies, doing some in situ DIC and some neutron diffraction studies to understand the strain localization on these horizontal samples along the prior beta grain boundary, and then we could actually assess whether what is the real culprit on the lower fatigue performance of horizontal samples.
Yeah, thank you for your response. Of course, going to the material aspect, it can be a little bit challenging to check what exactly is happening in the grain dimensions, but mechanically explaining, we can say when the vertical samples are showing higher ductility, that means that during the loading, we may have potentially higher plastic deformation.
Yeah.
And as you know, for low cycle fatigue, the majority of the life is being spent on fatigue crack growth instead of fatigue crack initiation. So this possible higher plasticity in the vertical samples that we saw also from the tensile data, it can create stress shielding in the material. And that stress shielding can result in this higher fatigue life that we have obtained. At least this is my interpretation.
Yeah. It's true. Thank you.
Thank you. Professor Stample, please.
Yeah, I think your presentation is a good add-on to also to the plenary talk, and that's what my question is referring to. So we saw in the first plenary talk the importance of defects, and that in SLM these defects, they seem to be hard to get rid of. So in your view, with your technology compared to SLM, do you see fewer problems with such defects? So is it easier to get rid of such defects, or what's your view on this topic?
Yeah, thank you very much, Professor Jürgen. We have built a number of walls using different deposition strategies using this technique. Because of the nature of this direct energy deposition AM process, as long as if we could able to maintain the good quality wire, I think we be able to eliminate these defects. However, whenever we have used some low quality wire, we have actually seen some defects in these material, particularly gas porosity defects, that is mainly attributed to the quality of the wire. On the other hand, SLM, there are couple of concerns with the SLM process or any powder bed process, where the powder quality might influence, and also some sort of process instability during the deposition will also influence overall the defect formation. So I'm not sure whether we can directly compare both processes, because fundamentally they are both different. But I'm not sure if I answered your question or not.
So might still need some investigation, right? The answer is not straightforward. Yeah. Okay. Yeah. Thanks a lot.
Thank you so much for your presentation. We can move on to the last presentation. It is titled Experimental and Numerical Analysis of Fatigue Cracks Emanating from Internal Defects in TI-64 SLM. It is presented by Mr. Santiago Montero.
Okay, hello. Can you hear me properly?
Yes, please, if you can give us a short introduction on your research.
Okay, perfect. Let's see if I can share my screen. Okay, can you see it?
Yes.
Okay, perfect. So, okay. So in the present work, we 3D printed a prismatic, rectangular shape titanium alloy specimen, and a group of those specimens were subjected to laser pinning, and another group received shot pinning. So the aim of those technologies are to implement or to set a certain compressive residual stress profile that basically changes the way the cracks are going to behave in our specimen. So in most of the cases, we are going to inhibit, thanks to the to these superficial compressive residual stresses, we are almost inhibiting the superficial crack initiation. So we are forcing the cracks to initiate from the interior or the internal defects, which is kind of curious because in most of the works they are trying to inhibit this this to happen, and we are trying to force it to study how it behaves. So the main goal of the present work is to understand how the cracks emanate and evolve from an internal defect in a fatigue test of this titanium alloy in selective laser melting. So we measured, of course, the residual stresses that you can see on the figures down in the slide, and we tested the specimens in 4-point bending, which is, I think it's an important fact. We can later discuss it in the questions if you want, because this tries to avoid some problems. This 4-point bending setup tries to avoid some problems with the alignment of the tensile tests. So we can discuss it later. So, well, let's start by analyzing the fracture surfaces of the specimens. What the first thing you see when you look at these fracture surfaces is a very bright region with an elliptical shape very close to the specimen surface. You can see it in the upper left-hand side of this slide. Inside this bright region, there's a particularly large defect, which you can see at the bottom of that previous figure. So you can imagine the complete evolution of the crack as emanating at the periphery of this internal defect, then growing in an internal elliptical way until it touches the free surface of the specimen. Then it becomes a superficial crack and keeps growing until it reaches the final failure. So in all that process, in all that evolving process, we saw 4 different regions in this fracture surface. So the first one is surrounding in the very first 300 microns around the defect, and you can see it's labeled A, and it's a very microstructurally textured region. So you can clearly see how the crack evolves following the acicular martensitic structure of which is typical of these titanium alloys. Next, as we go farther from the defect, we observe a very irregular region, which is labeled B, and you can see any striations there. And we hypothesize this is because the 2 faces of the cracks are smashing each other, and that's promoting crack closure. Then as you go to the limit of this bright region, you start to see progressively more and more striations, which you can see in figure C. And last, as you go farther from this bright region, you just find the final fracture. So we think it is, well, and we found this pattern in all these specimens that we analyzed. So it's interesting to go deeper into the defects. So we analyzed with a scanning electron microscopy and also with confocal microscopy both sides of every defect that we found. And also we extracted from the confocal microscopy image, we extracted a vertical profile of the specimen, which you can see in the bottom left-hand side. So in that figure, the vertical axis is perpendicular to all the other 3 figures. And the horizontal axis is represented by a white line in the bottom right-hand side figure. So you can imagine the complete 3D shape of the defect. And this one is a very curious example because we usually label the defects in 2 different types. We say they are crack-like if they are very sharp, or they are blunt. But in this case, we see a combination of the 2 situations. So next, now we, after we analyzed the defects that caused the failure, we try to build a numerically simulation model to try to obtain the same results that we saw experimentally, to obtain them numerically. And if you have any questions about it, we can discuss it as long as you want. So that's all for me. I think it's time for the questions.
Thank you, Santiago, for your presentation. On this topic, if there is any question from the audience, you can also use the chat to write your questions, and then I will ask the presenter. Yes, please.
I can say, It's Rhys Jones here from Australia. I just wanted to say to the young man, he's done an excellent job. I think that his work was great. I liked his presentation. I liked his numerical analysis. I can speak in technical detail fine, but I thought it would be worthwhile patting a young man on the back. So at that, I'm going to shut up.
Thank you for your comment, Professor Jones. If there is any question on this presentation, the topic was quite nice, and the technique that you used to capture the geometry of the defect, it was impressive the way you got a path from a 2D path that you have defined, and then putting it together and having the geometry of the defect. It was quite nice and creative. The defect that you had in your material, it was a lack of fusion defect. And this type of defect, they have this high aspect ratio, being more planar rather than spherical. Do you think in case of spherical defects, you would get also the same range of accuracy from having the simplification of a crack-like defect or not?
Yes, indeed. I can show you a few more examples, because this is the example we saw right now, but I brought you here another one.
Okay.
This is clearly a blunt defect.
Yeah.
So we applied the model to both situations, and actually the model is composed of two different parts. For those defects that were considered crack-like, that were very, very sharp, we didn't consider the initiation. So we considered that this defect would behave as the initial crack, and it would start propagating right away. But in the other case, in the blunt defects, we did include this initiation. But we came to the conclusion after all the simulations, I can show you here. If you see in the left diagram, if you compare the red triangles, which is the complete initiation and it's just the other way around. The red, the black triangles model the complete initiation and propagation model, and the red triangles model what happens if you consider that this blunt defect behaves directly as a crack. And we can see that the defects are very similar. They are almost the same. So according to our results, we were able to consider all the defects as crack-like.
Okay, thank you. There is a question from Mr. Harry Siho. Yes, please.
I want to ask two questions to Giovanni. The first one is your prediction approach is fracture-based.
Mm-hmm. Yes, it is.
And
we integrated a Paris-type crack growth law.
Very fine. How did you model the defect? At first, what's your method? And secondly, how did you model the defect?
So the defect has a very irregular shape, obviously. So it's very hard to model it right away. So we made the assumption that it was close to an ellipse. So we measured the area of the defect, and we tried to obtain a rough estimate of the aspect ratio, and we modeled an ellipse with the same area and a similar aspect ratio. And then we calculate the stress intensity factors using a weighting function methodology, which is important because we have a bending setup, so the tensile stresses are not constant in the section, but we also have residual stresses. So we had to use this weighting function methodology, and we calculate the stress intensity factors at critical parts of the crack, and that way we can see how every part of the crack is growing in the different directions, and the shape of the crack grows and also changes the aspect ratio.
Have you used finite elements or an analytical, a delta K solution?
It was analytical because the geometry was simple enough so that we could find the wave function, the proper wave function for the problem.
have you used any software tool?
No, we programmed it by ourselves in MATLAB.
Very fine. Okay, thank you. Just to clarify your model technique. My questions had this character.
Thank you.
Thank you. Any more questions from the audience? I have just one last question. In the slide that you were presenting the equations that were used, the first one is, if I'm not wrong, the NASGRO equation, what we know as NASGRO equation.
That's correct.
And usually the constant for this, we find it either in the literature or in the software called AFGRO.
Yeah.
How did you find these material properties for this AM part that you tested in the lab?
We found a few papers in the literature that were specifically related to additive manufacturing.
Okay, and they calculated the constant for this equation.
Yep. Exactly.
Yeah. Okay. Perfect.
They should be at the end in the bibliography. I don't think that if they're there, but they should be there.
Mm-hmm. Thank you. I will refer to that. Thank you very
Excuse
much for
me.
your presentation.
Excuse me, just a question more, because I got, I think it right now. Your model is independent of any R ratio.
Sorry, can you repeat, please?
I mean, your fatigue life estimation model is irrelevant of any R ratio. You can use it for R 0.1 and R 0.2.
Yes, we included that in the model because this changes the, well, first of all, the crack closure. That is a very important effect in our simulations. So it depends on the R on the load ratio. So yeah, this was included.
Thank you.
Thank you.
Thank you for your presentation, Mr. Montero. We can check if the first presenter is here. The first presentation was titled Selective Electron Beam Melted Non-Weldable Nickel-Based Superalloy, presented by Bu Chen. Any of the co-authors present in this room? No. Okay, so we have had all the presentations. Thank you again for the authors to present their work and for the participants to be here and ask their questions. It was a very nice and pleasant session. I hope you enjoy the rest of the conference. Have a nice day.